question that have to do with projectile motion problems, but aren't necessarily projectile motion problems on their own. They've got stuff about projectiles. For example, one of the things that we've already discussed, but didn't really talk about it in here for this problem or this kind of problem, is that you could still be asked all the kinematics questions that we had last week or the week before. So things like, if you launch something from the top of a building and it travels up into the air and travels down like that, there's going to be a place where the object is at its maximum height. So when the object is launched, one of the things that you need to kind of keep in mind is that the object's horizontal velocity at all points in its flight are all going to be the same. That part doesn't change. So Vx stays constant the whole time. So this object never has a velocity of 0. It's always going to have some horizontal velocity. But at launch, it has a vertical velocity that's being acted on by gravity, and at one point, that vertical velocity will be 0. But of course, also that vertical velocity is very likely to change directions. So there's a whole group of other kinds of questions that could be associated with projectile problems. One of them could be, does your object reach a height sufficient to clear an obstacle? So if we're talking about maybe a golf ball trying to make it over a tree, well, you would have to know where the tree is. You'd have to know how high the tree is, and then maybe figure out if the object is high enough when it reaches that point to clear the tree. Those questions aren't going to be easily solved by just looking at a chart. Those questions are probably going to involve you figuring something out about where the object is and how high it is above the ground. You have relationships that help you deal with how high the object is and where the object is, but these are both related to time. So in those problems, you're often figuring out, well, if the tree is here and is this tall, I need to figure out how high the object is when the object is at that location. That's not particularly hard to do. You figure out how long it takes to get here using the horizontal velocity, and then figure out how high it is. But you have to kind of put that together in your own head. I mean, you'd have to figure out a way to get to the problem. But what you really have are parametric relationships. You have relationships about displacement and relationships about position, but they are both based on time. And where the horizontal one is based on just Vx and t, the other one is based on a variety of potential things, but generally it's based on that. Now, there are other ways to look at this, and one of them is a little bit more complicated. It's called trajectory. Anybody know what the word trajectory means? Go ahead.
Like the path of how an object travels.
It doesn't have to be predicted. The word trajectory merely means the path the object takes. We could maybe predict it, but it is the path the object takes. So when we talk about a trajectory, we're not talking about a relationship with time. We're actually talking maybe displacement as a function of, vertical displacement as a function of horizontal displacement. Like if I could tell you where the object is at every moment in time, I might be able to tell you how high it is when it's 10 meters away, or how high it is when it's 20 meters away. That would be a trajectory equation. So I'd like to show you how you get a trajectory equation. To start this, I want you to understand what we're going to do is something we've already done before. We're going to try and eliminate t between these two functions. In fact, what we're going to do is assume just a standard object is being launched. I'm going to say that we've got a delta x, a vx, and a t. I'm going to say we're going to give the object some initial launch velocity and launch it at some angle. So I'm going to establish that x minus x naught is equal to v naught cosine theta times t. That's the horizontal side. And I don't know where, we'll just assume it's launched from an origin. I think that makes the most sense. But on the other side, delta y, vy naught, vy, a, and t. If we went ahead and made up positive and to the right positive, which was implied when we talked about the horizontal stuff, but maybe less implied now, then I could probably say that, well, the object may have some kind of vertical displacement, but I'm going to leave this as y minus y naught. I'm going to say that I have a positive v naught sine theta. Doesn't have to be positive. You can fire something downwards at an angle. It'd be called the angle of declination is often the word used there. If you've never heard the word declination before, it means downwards angle. So it's just like incline, but incline is can cover both. So when we talk about like accelerate and decelerate, inclination and declination have similar kinds of relationship there. We're going to say the acceleration is g, but we're going to say it's negative because we're choosing upwards and gravity is acting downwards. So we'll put an explicit negative sign there. If I wanted to come up with a relationship that had time in it, I would probably use y minus y naught equals 1/2 negative g t squared plus v naught sine theta times t. Now, this is two equations and two unknowns. I could take this equation and solve it for t and plug it into the other relationship. In fact, that's exactly what I'm going to do. I'm going to assume that the launch position is the origin. I'm not going to assume it here because the object could be launched higher or lower than the reference level, so I'll leave the y naught in there. But saying x naught is the origin makes okay sense. And I'm going to solve this for t and get x over v naught cosine theta. Now this next part is just hideous. There's no way to sugarcoat this. This is going to look ugly. But we're going to take this and put it over there. So y minus y naught equals 1/2 times negative g t squared. Oops, putting it in for t. Negative g times t squared plus v naught sine theta times t. And t was x divided by v naught cosine theta. Now, there's nothing potentially pretty about this. In fact, it looks hideous all around. Except this v naught is a constant. It's a launch parameter. Cosine theta is a constant. It's a launch parameter. G is a constant. It's a launch parameter. But x is a function. It's where it is horizontally. On the other side, I have a constant, where I launch it from, and the other function variable, which is how high it is. So what I want to do is rewrite this, but I want to collect all the constants. For example, I'll start at the beginning. Y minus y naught equals, I'm going to pull this outside of the x squared and put it with the constants. So I'll get negative g on top and 2 v naught squared cosine squared theta. Are you guys aware that cosine theta squared can be written as cosine squared theta.
Yes.
Just making sure everybody's aware of it, because I've met some students this year who were not. So if you were not aware of it, that is the way it could be written. And it's the way I will write it when you square a trig function. So if you didn't know that, please know that now. Now this is all times x squared. Plus, I have v naught sine theta divided by v naught cosine theta. The v naughts cancel, but that gives me sine theta divided by cosine theta times x. You guys all know that sine theta divided by cosine theta is tangent? Is that true all around? Do you know why? Did somebody prove it to you and show you? So you don't know why? You just accept it as truth? My word. I'm glad to see you guys accept so many things as truth. I guess you just want to pass a test. I want you to be better than that, or at least smarter than that. So let's prove why it's true, because you guys are smart people. You guys believe that, right? If I basically divide both sides of this equation by cosine, I get two fractions, right? The left fraction is sine theta over cosine theta, but the right fraction is a compound fraction. I could multiply it by 1, right? Hypotenuse over hypotenuse, which would be the number 1. And the hypotenuses cancel, and I get opposite over adjacent. Is that a good enough proof that that's why it's tangent? So now you know why it's tangent? All right. Smarter every day. So now I know this part's going to be hard, but, or maybe you won't see it, or worse, or maybe better for you, maybe you won't care. I care. So I want to wrap all this and color code it. Everything in white is a constant. It's a launch parameter. It's something that happened at the time of launch. Do you clearly see that this is y equals ax squared plus bx plus c? This is called the trajectory equation. It's not particularly important. What it does prove to you, or should prove to you, is that all projectiles have a path that is quadratic or parabolic. That the actual path taken by a projectile will be a parabolic path. It's not an arbitrary, it's not just curved, it's not circular, it's parabolic. It is specifically that function. If you graph this, you have a map of where the object is for every position. It doesn't tell you when it gets there, but it tells you the path the thing is going to take. So if you're ever asked, will this object clear the tree? If you put in where the tree is, it will tell you how high the object is. So it is a trajectory and can answer a certain subset of questions. Now, you may not be able to do it that way. You may still filter it through the time, and that will work. It's okay to do it that way. But this is in your capabilities. It's not easy, though. And I was talking to some folks in sixth period about this because they're a little bit ahead of you. And one of the things I did try to promote is that you could solve this for a different variable. For example, if you wanted to know if you could hit a target, you could solve this maybe for the velocity to see if you'd be able to hit a target, right? How fast would I have to shoot something to land at this location? You could rearrange this and make the functional variable a different variable. What you can't easily do, and I hope you see it, is you can't easily figure out a launch angle. Do you guys see that? It'd be very difficult to isolate theta in this relationship. So it'd be hard to say, what angle would I have to launch my projectile to hit that target? That might be a hard question to answer. In fact, that might be an impossible question to answer. So I'm going to ask you to do something in a minute, but I want you to know that this is out there. And now you know how to solve for it. You have access to it. It will actually solve one of your homework questions. There's a couple of ways to solve a couple of your homework questions that aren't this, but there's a couple things you can do. This is one of them. Now with that, I want to go back to the original picture we had here and remind you about a few other things. If you're asked what the maximum height of a projectile is, you still have a way to figure out the maximum height of a projectile. You'll have to change how you use your setup, but the maximum height of a projectile is going to be when the y velocity is 0. And I have y naught there, but it should just be the y velocity, not naught. It should just be vy. You set the y velocity to 0 and find out when that happens. And from there, you can figure out how high it is. Clearing an object, you could use the trajectory equation, or you figure out when it's at this location, and then figure out how high it is at that location. But since I've done all the work so far today on this, so you are an expert, you have it all in front of you, you know exactly what I asked you to do. So I want you to do it and to ask you to do something for me. Because one of you is not listening very closely. And truthfully, I don't know who you are that's not listening very closely, and I'm not going to turn around and find out. But you're going to go home the night before the homework is due, and you're going to turn to the internet, not knowing that I wrote those questions, so their answers might not be as easy to find. And you're going to ask the internet, how do I find the range? Because you didn't take particularly good notes. And the internet's going to show you something that's going to be what you think is super helpful. And you're going to ask Mr. Shelton, why didn't you tell us about this one equation that does everything? And I'm going to tell you why it doesn't do everything, but you're going to prove it to yourself. So here's what I'd like you to do. I'd like you to assume that we are launching something near the surface of the Earth, and it's going to land at the same height. So this is a type 2 problem, which means delta y is going to be 0. I would like you to find the trajectory equation for this. I want you to do the exact same thing I just did in front of you, but this time, instead of solving it for y, I want you to solve it for delta x. So we did all of it again, but this time delta y is 0, and I want you to solve it for delta x. You'll need to make your structure there, split out your v naught into v sine theta and v cosine theta, solve the horizontal side for time, plug it into the vertical side, and then tease out delta x. I'll give you 2 minutes, and then I'll pick on a couple of you to kind of tell me what you've gotten. Since I know some of you have no idea what I asked you to do, I just did half of it for you. All right, so in the interest of moving forward some, did you solve this one for t? Did you maybe set up one over here? I mean, this isn't very much, right? Same relationships over and over again. Now you're going to take this and use it over there. So I think it looks something like this. Is that what you guys did? Now, you could make this a lot easier on yourself. It was a t squared and a t, and there's a 0 here. We could factor out one of the t's, which would effectively cancel this term and take the 2 away and make it a 1. That would certainly make that look nicer, wouldn't it? So I will do that and get negative g delta x over 2 v naught cosine theta plus v naught sine theta. And I said to solve this for delta x. It's just algebra. So solve this for delta x. How about I take this term and move it to the other side of the equation? You all okay with that? It's negative. It'll move it to the other side, it'll be positive. So g delta x over 2 v naught cosine theta equals v naught sine theta. That all okay? I'm just trying to solve for delta x, so I want to get it on one side by itself. So how about I multiply both sides by the denominator here? We all okay? All right, so when I multiply by the denominator, 2 v naught cosine theta, 2 v naught cosine theta. That gets rid of the denominator there. I get g delta x on this side. I'm going to combine the two v naughts and write this as v naught squared times 2 sine theta cosine theta all over g. Oops, not over g yet. But now I'm going to divide both sides by g, so this is all over g. That's what I asked you to do. It's just algebra. I know. Some of you, this is no big deal, and you're wondering why I'm taking all this time. Well, look around the room at all the people still writing. Those are the people who did not know how to do this. And since nobody's looking around, that suggests that's a lot of algebra. This isn't particularly useful, but you will find something on the internet called the double angle theorem. I know some of you know this. Who's heard of the double angle theorem? So I have one hand, so maybe not very many of you. They start by this. They look something like this. Sine of A plus B equals sine A cosine B plus sine B cosine A. Has anybody seen that before? Okay. If you replace B with A, you get sine of A plus A equals sine A cosine A plus sine A cosine A. Follow me so far? The left side becomes sine of 2A, while the right side is 2 sine A cosine A. Do you see why I brought this to our attention? Do we? Does everybody see why I brought it to our attention? I have a 2 sine theta cosine theta here. It seems like I could make a substitution to just sine 2 theta. This is called the range equation. And if you look up range equation on the internet or how to do projectile motion problems, this comes up all the time. I want to remind you, this can only be used when delta y is equal to 0.